Good afternoon. My name is Kelly Paffel. I'm Technical Manager for Swagelok Energy. Today, I would like to present a presentation on steam system reliability. The reliability areas I'm going to be talking about is number one, steam leakage, and two, component failure. Steam leakage. In the area of safety, energy emissions. When we talk about leakage, people always think, oh, it's energy, but it's more of a safety item. The other thing is I want to talk about today is component failure, downtime, loss of production, maintenance hours. Everything that we put into a steam system today must last 6 years. But in order to achieve that 6-year reliability, a number of things must occur. And the biggest thing of any reliability program, the most important thing is change. Things must change. The way we did it 10 years, 15 years, even 5 years ago is not how we can do it today. We must demand reliability of all components that we put into the steam system. In order to do that, a number of things have to change. So if you're ready to have change, then things will dramatically improve into the steam system. One area is steam leakage. The steam leakage has a negative effect on a steam plant operation. Number one, safety, energy losses, increased emissions. And one of the things people forget about is the emissions. So if I go out and fix a steam leak, how many tons of CO2 will I stop being put up into the air? The other thing is also loss of reliability, and the thing a steam leakage does is cause production issues. So those are some of the areas we want to take a look at. Energy losses. Yes, energy. Energy losses can be as high as 19% or even higher in a few cases, the total steam energy production costs. So in doing analysis for steam leakage in plants, unfortunately, we've seen over and over again as much as 19% of the energy produced is lost through steam leakage. So if I had $1 million fuel budget, 19% would be contribute to $190,000 in energy losses. A tremendous amount of energy to be lost. The greatest payback of all items in the steam system is steam leakage correction. And we talk about doing this or doing that in the steam system to improve or optimize or improve the steam system thermal cycle efficiency. One of the biggest and greatest payback is steam leakage, greater than steam trap repair or replacement. People always say, oh, put out there, correct the steam trap failures, it'll save you all this money. Steam leakage is far, far higher payback than steam traps, insulation, or et cetera. So the thing is that if you're looking at to optimize the steam system, steam leakage is the number one or maybe even number two area that you want to take a look at. Steam leakage versus compressed air leakage. A steam leak on a yearly base would cost $3,591 at 100 psi-G, and that's 1/8 inch leak. That's based on $10 per 1,000 cubic feet. Steam leakage is an immediate savings. Compressed air leak would cost $2,095, 100 psi, 1/8 inch leak, and that's based at 0.05 per kWh. Now the thing about that is that a steam leak, if it's corrected immediately, is a immediate savings, whereas compressed air, if you go out and fix the leak, really the savings is you find enough leakage to remove an air compressor from operation, and then you get the bulk of the savings. Going out and just finding an air leak, correcting it without shutting an air compressor down and achieving the electrical savings, there's not much in the savings. So steam leakage is immediate savings. Estimating steam leakage is difficult. You need to know the size of the leak diameter. And of course with steam, it's very difficult to tell the leak diameter. The other thing is all equations are based on a perfect orifice, P1 being the operating pressure and P2 being atmosphere, which is the downstream pressure. because it's not a perfect orifice, and leakage is a crack on a piece of steam piping or flange leak or a thread leak. It's not a perfect diameter. Therefore, we use different types of equations to come up with the estimated steam leakage or cost. Here's an example of a steam leak. It's, 6 inches. We always call it the plume. I get asked all the time about, can you estimate the leakage by plume length? The answer is no. It depends on pressure. It depends on the diameter of the leak. It depends on a lot of things. But we had measured this through flow measurement, and distance was about 6 inches. The valve size was 3/4 inch. Valve opening 1/3 open. And so we estimated about a 1/4 inch leak. The pressure was 140 psi. What the cost was $14,367 a year. That is one leak point. Another one there, as again, we find this a lot in steam leakage, is valve failure. The distance was measured out to be 14 inches. Valve size 1/2 inch. Valve opening was 3/4 inch or 3/4 way open. 3/16-inch leak was estimated. Pressure 150 psi. Cost was about $11,605. So just on 2 applications, you see the savings is about $20,000, which again is immediate savings. Another leak, 40 inches in length. Leak was 3/16 inch, 250 psi, $18,651. The thing about steam leakage is the leak is this diameter day, but it will increase day after day because steam will wire draw the pipe leak point and increase in diameter. So the thing about steam leakage, you have to be extremely proactive. So we cannot tolerate steam leakage in a plant operation. The calculation, just to use a variation of Napier's equation for flow through an orifice, there are many different variations. So most equations are very aggressive for flow rates. Steam loss, we typically use a 22.88 times pressure absolute times diameter square. The 22.88 is a constant compensate for the imperfect orifice. No matter how you do it, it is estimated on the steam loss because, again, the orifice is not a perfect orifice, so you cannot use P1 and P2 in the equation. So anyway, this turns out to be a pretty conservative estimator for steam leakage. So if we take a look at this chart, there's a 1/16 inch leak, 100 psi. The steam loss, energy loss per year is going to be $897. So at 250 psi, $2,000. The thing is that if I go up to 1/8 inch leak and 100 psi, it's $3,591 per year. Also, part of these calculations is the emissions. How much emissions will be saved or stopped if I go out and fix the steam leaks. Here is a chart I pulled out from EPA, and I have a lot of information from the EPA on CO2, NOx, SO2, mercury, other emissions derivative from the fuels being burnt in the boilers that generate the steam. So if I was burning coal, the factor for CO2 per million BTUs is 205 pounds. If I was burning natural gas, it would be 117 pounds of CO2. So the thing about that is that by going out fixing leakage reduces the emissions that we're putting up into the atmosphere. A lot of projects in the recent years have been totally for optimization on emission or emission reduction because the plants are in a containment area and they need to reduce the emissions. So the other thing, aspect, safety, emissions and energy all play into, correcting steam leakage. One of the things you always have to ask yourself, what causes steam leakage? Number one, corrosion, CO2 or oxygen corrosion. And the thing about it is that in the steam system, we always blame CO2, carbonic acid, for causing all the leaks in the steam system. But don't forget about oxygen corrosion. On root cause analysis and any correction, part of your change is a very aggressive root cause analysis program to understand what caused failure. So doing root cause analysis, you will find that CO2 corrosion, sometimes there, but oxygen corrosion probably is going to be a more dominant player in causing steam leakage. So you must look at oxygen corrosion. Installations. Excuse me. The thing with this is that you want to stop steam leaks, stop threading pipe. You know, one of the weakest part of the piping system in steam or condensate is the threads. And the first place that corrosion is going to attack is the threaded connections. So today, installations in steam or condensate, we don't thread pipe. Everything is welded, flanged, or tube connectors. Components selection. You know, what are the components we're using? You know, still today, a lot of people are using the same standard packed valves for steam. The last great revolution we had on packed valve was 1941. So the other weak point into valving, besides the thread connections, is the packing. So you want to look at your component selection going away from standard packed valves to other type of valves today that we have available for us in the steam system. The other is operation, steam system operation. People have a tendency to have water hammer in the system, which is doing damage to the components in the steam system and causing leakage to occur. Steam component failure, threaded connections, valve flanges, heat transfer components, condensate lines, etc. Those are the areas we find the failures. Threaded connections, again, valves, flanges. The thing people tell me is flanges leak. Flanges do not leak. You have to know the torque pattern, the torque specification when you're torquing them down. Condensate lines should be stainless steel, but we're still using carbon steel. If you use carbon steel, then you should use at least Schedule 80 for the piping. Steam leakage will create safety issues. You know, people do get burned from steam. You know, condensate dripping down, extremely hot, burning people. These are injuries that over and over people occur in the field. Foggy conditions or fog conditions for visibility. Steam condenses to condensate, creates water in the air. Cooler climates, condensate will freeze and cause hazard conditions, ice buildup. So there's a multitude of safety issues that we have to, resolve and not have available to the plant personnel. So steam leakage we must correct. A roadmap for leakage: no more than 6 leak points per year. Eliminate thread connections. Eliminate standard packed valves. Change to component selections. The changes to component selections, selecting components that are not prone to leaks, like packed valves, larger valves, going to different types of valves, butterfly, ball valves. The fourth thing is installation standards, having a standard when we put the components in. So always the components go in the correct way. So there's your roadmap for correcting steam leakage. But I'm quite serious that no plant should have more than 6 leak points per year for steam leakage. We have the technology and the way to stop steam leakage. The other reliability issue is component failure costs, downtime, maintenance dollars, production losses, etc. If I lose a shell and tube on the process, I take the shell and tube down, plug tubes. That's costing me downtime, maintenance dollars. I'm losing production. For example, this is the picture here showing a failure. the tank rail car system. Number one, safety issue, steam blowing out. Two, we had to isolate the whole area, shut down the offloading of the rail cars, and correct the issue. Another one here is typical steam hose failures. One of the things I want to, make a statement on, steam hoses need to be rated to B31.1, the National Power Piping Code. We have most hose failures that we find with steam leakages. The hoses are not rated to B31.1. And make sure that every component you put in the steam system is rated to B31.1, the National Power Piping Code. Example of component failures like a tracing system, valve gives away, steam's blowing down, steam blowing out will cause a pressure drop. When you drop in pressure on steam, you also drop in temperature. When you drop in temperature on a tracer, you will cause production transfer issues. Again, here we come back with result is downtime. The thing that we can leap forward is downtime. So the thing is that component failure plays a critical part in production and eliminating downtime. Valves, standard pack valves, threaded connections, internal leakage. The thing with component failures like on a steam valve is we buy valves that already leak. You must be buying valves that don't leak. And the valve leakage rate is per FCI or ANSI standard or the API standard. So when you're buying valves, make sure you buy valves that are class 4 or higher that do not have a high internal leak rate. So if you're already purchasing a valve without specifying an internal leak rate, you get a valve that looks like this here in the picture, steam coming out of it. Component failure is heat transfer tubes. We have tube failure, we're always plugging tubes. PRV valve failures. Pressure reduction valves, again, should be 6 years minimum operation without any problem. But you have to remember a pressure reducing valve, a lot of them will go into critical operation. We must stop them from going into critical operation, and we must install correctly and select the components. Control valves, again, installing control valves correctly, making the correct selection. Do I use a cage, trim valve, globe? What does the internal look like? How do I operate, electric or pneumatic? Heat transfer components, what type of service? Plating frames are used in certain types of services. And certain type of services, they should not be used. Like a steam coil. Should I use copper tube or steel tube? Steam, you should use steel tube. Expansion devices. Having the device in the correct location, taking axial movement only will prolong the life. Turbine components, internal nozzles, buckets, blades, erosion, steam quality issues, cross component failures. Condensate pumps. Without having NPSH, the pumps will cavitate. And then we switch and we go to steam motor pump, which gives us a higher unreliable operation. Steam traps. Steam trap today under 250 psi should last you 15 years. You should not have component failures. The thing to increase reliability, number one, change must occur. And I said this before. Change can be engineering specification, system design, product selection, installation standards, operations per SOP, standard operating procedures. So the change is not going to be just in one area. It's going to come from all different areas, even in maintenance of the product. So to increase reliability in the steam system, number one, change must occur. This other thing I want to point out is steam losses, venting steam to atmosphere. We don't do that anymore. It costs too much money. The thing about optimization of the steam system, reducing reliability, optimizing it, stop venting steam to atmosphere. It's a major loss. So today what we want to see is no steam vents to atmosphere, no steam loss, no steam leaks, no steam losses to atmosphere, and a minimum of 6 years operation life for all steam components, which is extremely achievable, no problem. The other thing is our mission statement is we provide world-class energy service to help Swagelok customers optimize their in-plant steam and condensate operation. We do that with world-class services, customized training programs, steam system engineering, steam and condensate system design, project management, and consulting services, engineering support services. We are there to help you. Meantime, if you have any questions, you by all means can contact us or email us, and we're more than happy to help you.